Okay. Yeah. Okay. So everyone, last week, you also know that uh, to in order to get the stage, yeah, the equilibrium stage, you have to uh, draw the enriching section, and then after the enriching section, we try to sketch, and then after that we draw the stripping section, and after that, after the stripping section, we also check the condition of the feet, and then draw the intersection between the, so where is it, sorry, uh, yeah, and also the intersection, and then we can determine uh, the equilibrium stages for distillation. Okay, and now, but sometimes we don't really know also how to get the reflux ratio. Yeah, we can't put any value of reflux ratio. Okay, so because sometimes okay, I want reflux ratio, for example, 100. Okay, or reflux ratio, I want the reflux ratio, for example, 3 or something. Yeah, so how we sure that we have a good reflux ratio. Okay, so if we, okay, go back here. So reflux ratio, we define it as the slope for the enriching substages. Yeah, if we if or yeah, the no no the reflux ratio, I think this the enriching, I think it should be reflux ratio is the ratio between the liquid and also the distillate. Okay, can I read it? Okay, let me check, wait a little bit, this one here. Okay, just let me make sure that, okay, so it's the pen color. Okay, if you remember the equation, yeah, we know the, oops, go back here. We know that if you look at the slide again about last week, we know that for the operating line here, the top operating line, so we know that y n plus 1, yeah, n plus 1 equal to uh, r divided by r plus 1 xn plus xd divided by x plus r plus 1. Okay, so we know that this one is the equation, and then so the slope actually will have an intersection with the with the y-axis at, let's say, I, yeah, intersection xd divided by r plus 1. Okay, then let's continue. So here that the influence of r, if r is decreasing, I is increasing. If r is increasing, I is decreasing. Okay, so if we decrease the reflux ratio, it goes to just goes down there. While if we increasing r, I is also decreasing. So it really depends. Let's see. Yeah, let's check another one. Okay. Let's try. Okay, so let's have a look. This is an example. Let's say we have an example of that f equal to 0.4, yeah, and then this one is the a vapor liquid mixture. Okay, like maybe minus 1, yeah, 50%, 50%. So we know that f is actually equal to 0.4. So this is the the point of ZF. And then we want the distillate is around 0.9. Okay, so this one. So the distillate is 0.9. Okay, and then the bottom that we're gonna keep it at 0.1. So maybe around here, 0, 0.2. So 0.1 is between 0 and 0.1. Yeah, 0.2. Okay, so let's say when r equal to 2, yeah, just try to imagine, yeah. If I put the, okay, let's say the reflux ratio is 2, right? So okay, is actually xd divided by r plus 1, yeah, or the here I is the xd is 0.9 and the reflux sorry, r is actual equal to n plus 1, so it become here become 0.9 divided by 3, so that we got 0.2, simple set, yeah. And then let's just put the number 3 on the, which one here, around 0.3 there. Okay, if we calculate it, maybe this includes some animation, yeah. Let's say, okay, if we okay, where is it? No, okay. Let me check if this one is include animation. No, yeah. Okay, let's say what happened if the Q line is 0.3. Sorry, if the intersection is 0.3, so this one. Okay, 1, 2, 3, 4, 4.2. Okay, so the number is 4.2. Okay, however, if we cut it, for example, r equal to 8, so the amount of reflux ratio is 8, let's say, for example, so we increase the reflux ratio from 2 into 4 into 8, just let's say, so the intersection that is become yeah, it become 0.9 divided by 0.9, which is sorry, not 9, yeah, 0.9 divided by 1, 0.9 divided by 10, sorry, yeah, around r plus 1, yeah, r plus 1, it should be 9, yeah. Okay, this let's do an eraser. Okay, so it is actually 1. Okay, so and then if you have 1 here, okay, if you have 0.1 and then you put it here and then you calculate it, now the stages become 1, 2, 3 point something. Okay, so anyway, what can we learn from this a simple example? If we increase the reflux ratio from 2 into 8, yeah, this one, from 2 into 8, then the number of equilibrium stage, is it increasing or is decreasing? If we increase reflux ratio.
It's decreasing.
Yep, that's right, yeah. It's decreasing from 4.2 into 3.2. Okay, so it is decreasing. So that means that if we increase the reflux ratio, that the equilibrium stage number n is also decreasing. So that means if you want to decrease the equilibrium stage number, you just want to keep increasing of the reflux ratio. But what is the impact? The impact, you don't have much distillate, yeah. Remember, R is okay. If you look at here, uh, R is actually L over D, L over D. So if you increase the R, that means your liquid is also increasing. So you just keep looping, yeah. You just keep put the liquid going back, and then you only have small distillate. Okay, just small amount of distillate. But the impact is you have less equilibrium stage. Okay, what is the meaning of less equilibrium stage? One stage is has a, if we said for example, okay, if one stage for example around half a meter, so then two stage maybe only 1 meter, or so then you have a minimal amount of the height of the distillate, the column. Okay, that means the minimal amount of columned material, which is a minimum, actually minimum capital cost, yeah, capital cost. So this tells you, this graph tells you, yeah. I'm sorry, we can't really put it on the same line because it is looks like animation, yeah. But increasing reflux ratio means that your equilibrium stage is decreasing, which is also shows you that your tower is shorter. Yeah, tower is shorter, so then your capital cost is also shorter. But if you decrease the reflux ratio, so that means you increase the equilibrium stages, so the number of stages would be maybe increasing from 3.2 to 4.2. All right. Okay. So now, so what's the implication? So if if the distance of operating line to equilibrium curve is the increasing, this one, yeah, equilibrium line to the let's say this one is the operating line, yeah. Let's say if we put the operating line on here, really there, yeah, uh, really you know similar to the line y equal to x, this one there, then I actually become 0, this one, yeah. So I equal to 0, so that means xd divided by r plus 1 equal to 0, so that means r would be at infinity. Okay, so so actually, so that's this happens, it's called a total reflux condition. This is when we don't have any product, we don't have any distillate. Okay, that happens if we don't have any distillate, which is all of the vapor we condense it 100% as a liquid and then put it there, yeah. And then when reflux condition is called the minimum stage of equilibrium. Okay, minimum, the number of minimum equilibrium stage is called Nm, and how we calculate Nm is when R equal to infinity, or we call it at the total reflux condition. Okay, so by judging this curve and then have a look here. So the N minimum, or the stage of minimum equilibrium that when we calculate is actually about 1, 2, and around 3. Okay, so the minimum stage is 3 when the stages, or sorry, when the reflux is minimum. Okay, if we increase the reflux up to 8, go there, yeah. If we increase if we make the reflux into 8, the stage number is increased a little bit into 3.2. If we decrease again the reflux to 2, yeah, from infinity to 8 to 2, and then the number of equilibrium stages is 4.2. Okay, so again, increasing the reflux ratio, it's gonna change the decreasing reflux ratio. Right. Okay. I just want to check also. Book Grace, are you there? No, yeah, not yet. Yeah. Uh, Also, I will prepare after this. I will prepare some latihan, yeah, or uh, exercise, and then I'll give it after the class to Edu next, and then hopefully you can print it out, or you can have a sketch on Microsoft Word or PowerPoint, or it's really up to you. So tomorrow. Around 1 hour from 10 to 11, Bu Grace will explain to you some exercise about this. All right, next. Okay, now one more. Yeah. So first, so if then the minimum stage of equilibrium is happen when the reflux is infinity or maximum, yeah, in total reflux. However, if we just drag the line up there, yeah, the maximum of the top line, the maximum of the top line is would be between the intersection between the Q line and the equilibrium line. Okay, why? Because let's have a look on this one. If we have a Q line there, okay, and this is the Q line, and also this is the equilibrium curve. So if we have a top operating line that also intersect with the Q line, and also this one is the equilibrium line, let's have a look. So this is 1, and then 2, and then and then this is 3, and this 4, and this 5, and this 6, and 8, 9, 10, 11, 12. But it can't go to that size, yeah. It can't go that size because the between the operating line and also the equilibrium is almost similar. So it's just gonna stop in here up to infinity. Okay, so make it different color. Okay. So what is the okay? So okay, so they will just only up to here, yeah, only up to here, and then they won't go down to the which one is here, which is the bottom operating line, but they will just, because it's gonna keep going, it's just gonna keep going, and then from the equilibrium and operating line, equilibrium, operating line, ya, menuju tak terhingga. Okay, so that means if I is increased, the intercept is increased, and then R is lowered, this will result in an intersection of operating line, equilibrium curve, and Q line. And at this condition, I equal to I am minimum, intersection minimum is equal to intercept minimum equal to XD divided by RM plus 1. Okay, so we call it RM, or R minimum, or minimum reflux ratio. Okay, so the number stage is infinity. Okay, and it's happened at R minimum, or reflux ratio is minimum. Okay, so okay, so it's called RM, or reflux minimum reflux ratio. So sometimes in the practice we calculate the R, the reflux ratio, is based on the minimum, for example RM minimum, yeah, from the, for example, 1.2 multiply with reflux ratio minimum, the minimum reflux ratio. Okay, why that happen? Let's have a look. Okay. Okay, so we have to optimize the reflux ratio. Why? Because first, maybe let's look out the here, yeah. The this one is the, let's look at this one, which is the orange one. The orange one tell you the cost of the tower um, with the reflux ratio. Okay, if you increase the reflux ratio, you have lower stages, right? You have the lower equilibrium stages. Okay, lower equilibrium stages means your tower require less stages or less height, ya, tingginya berkurang. Okay, when the tower, the distillation tower have less stages, that means your capital cost is is decreasing, which is a good thing. Okay, you don't want to have much capital cost, of course. Yeah, if you can go to the lower as possible, that's very good. Okay, so that's a good thing. However, because if we increase the reflux, okay, if you look at the green one here, we're gonna increase the exponentially the operating cost. What is the operating cost? Because this means that the liquid will the vapor should be condensed, so the condenser cost, okay, the condenser cost, you need cooling water to moving around, okay, from the pump you need to cooling water to moving around, and then when you have the liquid, and then the liquid must be boiled up again at the bottom by the boiler. So you need the maybe fuel as well, yeah, fuel to um, to heat it up the boiler. Okay, so first you have to cool down the condenser, and also you have to boil up the boiler. Okay, so then R also correlate to operating cost exponentially. Okay, which is the condenser utility cost. Okay, so the increasing of R is also increasing operating costs. Okay, so then if we combine them together, the capital cost and the operating costs, then we have the blue one there. Okay, it's not really good if we go up there because we have a high operating cost. So then we have an optimum around here, and the optimum reflux ratio is about 1.2 to 1.5 of the reflux minimum. Yeah, that is based on empirical data. Okay, so then the optimum reflux ratio that we choose is around 1.2 reflux minimum reflux. Yeah, so later if the in the exam, if if it is not stated the how much is the reflux ratio, you can determine that the reflux ratio of the optimum ones is around 1.25 of the RM. Okay, so then you have to find the RM. You can find the RM from the sketch, right? Okay, so I think that's for the first session or first presentation, and then let me have a look on the next slides. Okay, meanwhile, um, any questions up to here, up to here?
Ibu, I have a question.
Yeah, okay, Nadifa.
To determine the n, the number of equilibrium stages, it's based on drawing the steps on the graph, right, Bu?
Yeah.
So how do you determine n if it's not an integer? Like in the example, it was
Right.
2.2.
Okay. Okay. Usually for the stages, for later for the exam, it is usually we have to put it in integer because it is a stage. Yeah, like I said before, one stage is like one two tray. Yeah? Like one tray is one stage. So you have to make that of your points of the equilibrium should be less than your bottom. Okay, so for this one here, you actually, this is actually tells you 1 stage, 2 stage, okay, the XB is still much lower, and then 3 stages. Okay, so this is, so it should be an integer. Okay, but this is, I think, for this one, yeah, this is just tell you in the practice, it should be, you have to apa, dibulatkan ke atas ya, you have to round it up, but this is just tell you that ideally ya, ideally you have 4.2 or 3.2, but in practice if you have this calculation you have to round it up to uh, uh, to uh, to a bigger number. Okay, is that answering your question, Nadifa?
So in exam, we also rounded up.
Yeah, you have to round it up there. So you have to make sure. So here, for example, here, yeah, the look at the maybe the green one. So the green one is would be 1, 2, 3, 4. Yeah, it should be 4 because when you have the 3, green is still less than the bottom that we want. So then we have one more stages. And then but this is much lower than the XB, that's fine, yeah, it's good. It's still good gitu, yeah, but it should be, yeah, this is the minimum for the B. Okay, and then for example here for the brown one, so that would be 1, 2, 3, 4, 5, 5 stages. Okay, yeah, any other questions?
It's clear from me. Thank you, Ibu.
Okay, then let's have a look. Okay, okay, this is the second one, and then let's check another one. Okay, so so this is gonna be the last segment, yeah, this is gonna be the last segment, and then that's why tomorrow 1 hour I will maybe just explain a little bit, check from the beginning, and then I don't know, yeah, is it quiz or is it latihan, maybe, yeah, maybe just some exercise, but yeah, but the next 1 hour at 10 o'clock, hopefully you can start checking as well, yeah. Okay, all right. Okay, well, let's go back to here, make a tail diagram. Okay, so first, what is the step to get the to construct the diagram? First, we have to locate the feed, all of the feed and also the product, yeah, the product composition that we want. Okay, locate the feed, ZF, also locate the product, distillate, and also the bottom. Okay, the next stage is also we can also draw the Q line. Yeah, we also draw the Q line there. So locate, I have a little bit of trouble with my Wacom, so it doesn't write really smooth. Let's have a look if I can, maybe I'll, okay, I'm make it, let's make it bigger there. Okay, hopefully this one's better. Let's make it full screen, maybe. Yeah. Okay. 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 So number one, you want to find your ZF, your XD, and also your XB. Yeah. Okay. Number two, you want also, here's the thing, for number two, you want to know also the Q line. Yeah, you want to know the Q line. Is it saturated vapor? Is it saturated liquid, or is it composition in between vapor or liquid together? Is it subcooled or is it superheated vapor, in order to get the Q line. Okay. Okay. Okay, this one you have those Q line. Now, the next stages, you want to find the intersect, you want to find the interception. Okay, what can you do? You want to find the intercept by checking the RM. Okay, when you have the RM, so first you have to maybe construct a line from here, from XD into the that one there, yeah, to the intersection between the Q line and also the here, yeah, this one there, and then go back there to get the RM, yeah, to get the minimum. So I equal AM equal to RM divided by XD plus 1. Okay, because so that, because if you draw a line, so maybe let's say, let me draw a line, shape line, yeah, let's make a line from here to here, there. Okay, everyone. Okay, so now I have this, yeah, this point that tells you about the RM divided by XD plus 1. Okay, so then I can calculate I can calculate RM. Okay, so you can find this one, you can find the intersection, the intercept when it's minimum, and then you can get the RM, yeah, using your calculator or using your hand. Okay, so, and then let's check your problems, your problem definition. What is your reflux ratio? Is it 1.2, is it 1.5, or is it 1.25? And then you can find the RM. Find R. My Wacom doesn't really smooth, so let's using a razor. Okay. So find R. Okay. Just multiply, for example, yeah, 1.2 RM. Okay, and after that, then you can make your new I, or the intercept. Okay, make your intercept, maybe for example this one. Okay, after this you just need to calculate it, and after this, then what you can do, you can start construct your distillation column. So this is one stage, yeah, two stage, three stage, four stage. When it passed the feed, so this is the tray feed, yeah, the feed tray. Okay, so then would be the enriching. So the enriching is 4. Okay, and then the downside after the enriching is the stripping, 1 2 3 4, yeah. So then you have stripping, stripping, actually 4. Okay, so you have 4 enriching and 4 stripping, and then plus with 1 reboiler. So then you have, so if you sculpt, well, how many stages of the equilibrium stages? So then you have 8. How many stages in the enriching? There are 4, and the stripping there are 4. Okay, and what is the fifth stage? Is 4. Okay, so that is the outcome, yeah, of your stages there. Okay, now let's continue. Okay, what is this? Okay, so what happened if we increase the reflux? I think this tell you before, yeah. From here, if it is start from, for example, 0.2 something, if you let me check a little bit. Okay, if you increase the reflux, it goes to down there. Okay, so that means it will lower your equilibrium stages, and if you reduce your reflux, you go that way, which is increasing the stages. Yeah, we learned this before, so I'm just gonna skip it. And then again, there is a total reflux when the operating line also similar to the x equal to y line. Okay, and there's also minimum reflux when the stage of equilibrium is infinity. Yeah, we knew before. Okay, so I just want to add one more example there. Okay, what happened if we have a typical line like this? Yeah, this is the normal one. Okay, this is the normal one that we can see, yeah, like in before. So if this is the normal one, then yeah, this is construction for minimum reflux at ideal reflux, for example. Yeah, this is a normal one. But what happens if we have a non-ideal stage? Yeah, if it's a non-ideal stage like this, so this is a curve of ethanol and water. Yeah, looks like this. How to determine the stages when it is the infinite stages? Yeah, how to find it? To find it, we have to draw. Let's have it. Let's draw. Okay, we have to draw a line. So let's say this is the line that passed the curve. Can you see it? This line is passing the point P. Okay, it can't be like that. Yeah, it can't be like that. No, because now it's just outside the equilibrium stages, so it won't work. So then what can we do is we have to put it there. Ya, so it should pass the point P. Harus menyinggung kurva. Ya, so to get the R minimum, this one is the XD per RM plus 1. To get that point, yeah, to get the point, you have to make a line that start from see, so it should be start from the distillate, and it should pass to a point P. Okay, so this is for the non-ideal system, but for ideal system, to get the reflux ratio minimum, you need to start, for example, let me draw it here. From here, yeah, from XD to the intersection between the curve and the Q line there. Okay, which is this one is the point P. This also the stage is infinity. This one also the stage is infinity. Why? Because at this point the operating line will be similar with the equilibrium line at this point. Okay, did you get it what I mean? So there are two type of graph. This is the normal graph, the ideal graph for xy diagram. This one is the non-ideal xy diagram. Okay, in the exam usually there are two type of sketches. Yeah? First one is the normal one, and this one is the non-ideal one. Okay, anyone want to comment about this? Maybe I want to ask Fatia. Fatia, do you understand what I'm saying about how to get the RM minimum, the minimum reflux?
Yes, Miss, I think I'm starting to get it.
Okay, yeah, it is difficult. It's really difficult to explain it here. Yeah, usually I always just write it on the board, so it's just easier to see. But basically, because to get the RM, you have to construct a line from the distillate into the intersection between Q line. This is the Q line, and also the equilibrium curve. Yeah, if the it looks like this, let's say, let's have a draw. Okay, boo, for example, I get it. So we have to construct a line between uh, uh, x distillate and reflux ratio with the Q line. But if you think about it, if you look at this line, yeah, if we stick to that point, let's have a look. If I draw, okay, if this is a Q line, yeah, this is the Q line. Let's make it bigger. Yeah, if that is the Q line, okay, boo. So we have to construct a line between Q line, intersection of Q line and also the curve. Okay, so if we started put it like that, and that one there, yeah, if we do it like that, is it good or not? This one is not the right way, because then you have a line that actually it's outside the equilibrium. Yeah, it outside the equilibrium. So so this is wrong. So what you can do is to have a line, construct a line from the distillate, and then you with your ruler try to find, yeah, try to find a line that uh, past the point P, which is the one that have just similar, yang bersinggungan. Cari garis yang bersinggungan dengan kurva. Okay? Yeah, that's just some points that sometimes we can get some exam like this. Yeah. Okay, what time is it? Okay, 10 more minutes. Right. Okay. Also, this one, a place for feed entry or the feed optimum. Okay, this one I'll continue tomorrow. I think, let me check. This one I'll continue tomorrow. And then, yeah. And then this also I would like to show you as well. So this is the data, how to get the reflux ratio of a representative distillation operation. From the Seder book, or this is from Timmerhouse, yeah, Plant Design Economic. So here is the reflux ratio. This one is the minimum reflux ratio, and this is the annual cost of the capital cost, yeah, the annual cost, sorry. And this one is the annual and fixed charges of the equipment. It decreased with the increasing reflux ratio, but the annual steam and cooling water also increasing as linearly at this time. So then the annual cost then also increasing. So around 1.25 from that one there. it would be the optimum one. Yeah. So here, as the refractive ratio is increased from the minimum value, the number of plates of the trays is going to decrease, the column diameter would increase, and the reboiler steam and also the condenser cooling water also increase. Yeah. But when annual fixed investment for column, condenser, reflux drum, reflux pump, reboiler are added to the annual cost of steam and cooling water, an optimal reflux ratio it would be established. So it's around 1.2 to 1.25. Okay. So again, back to here. Um, so in the McCapital analysis, which would be the outcome of the exam, would be, I think it should be next week. Yeah, the exam, the module one should be next week. The exam next Friday. Uh, so first, usually we have the TXY diagram provided, and also the feed, the composition, the temperature, the distillate, the composition of distillate, and composition of bottom also is defined in the problem. And then usually we want to find the R, that's the outcome, to determine the number of theoretical stages. Okay. And again, if we increase the reflux, then the number of stages would decrease. While we decrease the reflux, then the number of theoretical stages increase. So the the extreme between of those two reflux rate is first as a total reflux, where there is no top product withdrawal, or a minimum reflux, which we have a very very high infinite theoretical stages. All right. Looks like I'm gonna stop the recording, and looks like it's gonna